Any of the MIT integration will be qualifying exams 2013, which is indefinite integral of sine x times the natural logarithm of sine x. So this is a fairly intricate problem. So let's see how we may be able to solve it. So our problem is the integral, indefinite integral of sine x times the natural logarithm of sine x. Yes, and for us, I think trying to substitute that off is the trick. We would say let u be equals to sine x, and what that means is that du dx is equals to cosine x, and so du over cosine x is equals to dx from here. And cosine x is simply the same as the square root of 1 minus sine x, so this can be rewritten as, which means that du over the square root of 1 minus u squared is equals to dx. So this is an important substitution thing that we should have in mind. Okay, and so our integral sine x times the natural logarithm of sine x can be now written as sine x, we've let it to be u, natural logarithm of u, and then dx, we found that we can substitute with du over square root of 1 minus u squared. So this is the same as u over square root of 1 minus u squared, natural logarithm of u. Now, if you differentiated that, we would get negative 2u times, we differentiate what is inside here, times the square root of 1 over square root of 2 times this being their half, and so that cancels, and so we have negative u over square root of 1 minus u squared, right? So that is, this is a by the way, right? And so we can see clearly that this guy here is a derivative of this guy, but with a negative sign. So our problem now becomes, right? And so we can use integration by parts, and that is if you have a product of v and a derivative of capital U, integrated, you get uv minus the product of u times the derivative of v, right? So for our situation here, this happens to be our u, obviously with the negative, and this happens to be our v. So our integral now becomes negative the square root of 1 minus u squared, natural logarithm of u, minus minus becomes positive, square root of 1 minus u squared, which is u, times 1 over u, which is the derivative du. Yeah, just so that this is not confusing us, du is hiding there. So our problem now becomes negative 1 minus u squared, natural logarithm of u, plus the integral of square root of 1 minus u squared over u du. So this is interesting. I would like now to rewrite it in such a way that we have two integrals and we use color blue to demarcate our second integral. So solving our blue integral now, one thing we may be able to do is substitute this complex part with something else. So we could just say let y be equal to the square root of 1 minus u squared, such that y squared is equal to 1 minus u squared, and so 2y dy du is equals to, and these two cancel, so essentially y dy negative can be used to substitute for u du. Important. And since our integral is this, now becomes, in place of the square root of 1 minus y squared, we have y. In place of u, we have the square root of squared. But then, as we saw, maybe before we complicate things a little bit, let's try to play things around and focus on expressing it in such a way that the substitution is easy. So we have 1 minus u squared over u squared times u du. And so since we say that y squared is equal to 1 minus u squared, that means that u squared is equal to 1 minus u squared. Okay, so our integral now becomes, in place of the square root of 1 minus u squared, we get y. In place of u squared, we get 1 minus y squared. In place of u du, we get y dy negative. Okay, so now we get the integral of y squared over 1 minus y squared dy. Okay, actually square root, negative is there. So what is y squared over 1 minus y squared? That's the same as if we have y squared and 1 minus y squared, negative 1, we get negative positive y squared minus 1, and this is 0, and this is plus 1. So y squared over 1 minus y squared is the same as negative 1 plus 1 over 1 minus y squared. Okay, so we had found out that y squared over 1 minus y squared is equal to negative 1 plus 1 over 1 minus y squared, which is the same as negative 1 plus 1 over 1 minus y, 1 plus y, which is the same as negative 1 plus a half of 1 over 1 minus y plus 1 over 1 plus y. Splitting this fraction apart into partial fractions, which means that the integral of negative y squared over 1 minus y squared is the same as the integral, this negative interacting with this negative 1 minus a half 1 over 1 minus y plus 1 over 1 plus y, which when integrated we get, this becomes a half, and this becomes a half of negative natural logarithm of 1 minus y plus log of 1 plus y plus an intermediary constant. Let's call it C2, our integration constant. Our integral y squared over 1 minus y squared, we found it to be equal to y minus a half of negative log 1 minus y plus log 1 y plus C2, which is y minus, using the rules of logarithm, this means this is just log of 1 plus y over 1 minus y over C2. So, which is interesting because our integral of square root of 1 minus u squared over u was what we had come up, right? And since this part here is what was denoted as y, then that becomes the square root of 1 minus u squared minus a half natural logarithm of 1 plus square root of 1 minus u squared over 1 minus square root of 1 minus u squared plus the integration constant C2. Okay? Integral was negative 1 minus u squared natural logarithm of u, and then now we can shift to the next part, which is the integral of square root of 1 minus u squared over u, right? And this part we just found to be equal to square root of 1 minus u squared minus a half logarithm of 1 plus square root of 1 minus u squared over 1 minus square root of 1 minus u squared. We can close all this plus the integration constant, but coming back here we can just bring this top part there. But also we know that we had in the original substitution we had said u will be equal to sine x, and what that means is the square root of 1 minus u squared is equal to cos x. So what does that mean? What that means essentially is that our original integral of sine x, natural logarithm of sine x, is equal to where we have negative of a square root of 1 minus u squared, that's the same as cosine x, logarithm of sine x plus cosine x minus a half logarithm of 1 plus cosine x over 1 minus cosine x close plus the big integration constant. Now, for those of you who may be wondering where this is all coming from, this is coming from previously we had seen that our integral had come to a point where we have square root of 1 minus u squared log u plus bracket square root of 1 minus u squared minus a half log of 1 plus square root of 1 minus u squared over 1 minus square root of 1 minus u squared close bracket plus c. So this is where we are picking things from. And we had seen previously that 1 minus u squared is the same as cosine x. U was the same as sine x. So I'm sure we can simplify this further. And that comes from cosine x being equal to either 1 minus 2 sine squared x over 2, and also cosine x is the same as 2 cosine squared x over 2 minus 1. So if then we substitute, in the case of the negative we can substitute this, in the case of positive we can substitute this, and things become a little bit different there. So we have our integral of sine x, natural logarithm of sine x, right, being equal to negative cosine x log of sine x plus cosine x minus a half logarithm of 1 plus cosine x over 1 minus sine cosine x, plus c, which is the same as cosine x log of sine x plus cosine x minus a half log of 1 plus cosine x is the same as 1 plus 1 plus 2 cosine x squared minus 1 becomes 2 cosine squared x over 2 over 2 sine squared x over 2. See, so we see this cancel, and then this goes up, we get a square root, so we get to negative cosine x log sine x plus cosine x, and then when we flip things around it becomes log of sine x over 2, because we've changed the sign, over cosine x over 2. So this becomes tangent x over 2. So the final answer in the most simplified way becomes tangent x over 2 plus the integration constant. And that's, I think, a better, more simplified answer. So thank you so much for your attention. I hope you do enjoy following this. This certainly has been a long, protracted way of solving it. I know there are other simpler ways, but this seemed interesting for us.